Hello everyone, let's solve some Leetcode today. So today we have Leetcode 329, that is longest increasing path in a matrix. In this matrix we will have a few numbers and we have to find out the longest increasing path. For example, here we have 1, 2, 6 and 9. So this is the longest increasing path in this matrix. If you try to go some other path, for example you can start with 9 and you try to go in this direction, you will have a lesser number. If you try to go in this direction, you have the same number. In this direction, you have a smaller number. So you cannot go in any direction and find a greater number. It means the length of the longest path from 9 is simply 1. Similarly, if you start from 4, you can go in this direction and you will find 8. Now 8 is greater than 4, that's why we are here. If you try to go somewhere else from 8, suppose I want to go here, then I will find 6. It is not greater than 8, so I cannot go here. If I try to go down, it is not greater than 8, it is 1, right? So I cannot go down also. It means I can go 1 and then 2. So the length of the longest path starting from 4 is 1 and 2. This is the length. Similarly, we will have many paths starting from each of these cells and we have to compute which one is the longest path out of all of them. Now, before we try to find out the maximum path, let us try to make some observations. First of all, let us take this particular path. We are starting from 1, then we are going to 2, then we are going to 6, and then we are going to 9, resulting in a length of 4. Correct? It means the length of the longest path starting from this position is 4. Now, what about this position, the 2 position? What is the length of the longest path from here? Well, it will be 2, then 6, and then 9. Basically, the length is 3. So I can say the length from this position is 3 and the length from this position is 4, right? Now suppose that this number was not 9, it was 10. What would be the length now? If I start from 2, I will have this, and then finally this 10. It means that we will have 1, 2, 3 and 4 numbers. So now this particular position will have 4, correct? And now if I want to calculate the longest path starting from this particular position, I can simply do this. I can take the longest path starting from this next position, that is 2. So it will be 4 and I can simply add 1 for this particular cell. That will give me 5, right? Which is correct. If I start from 1, I will get 1, then I will go to 2, then I will go to 3, then I will go to 9, and then I will go to 10, which is equal to 5 steps. So it is correct. So this observation tells us that it is worth it to store the longest path from different cells or different positions, because we can use those stored numbers to calculate the path from other cells, which means we will not have to go through the entire path for each and every cell. Now the other concern is that what if there are some loops? If I can just go into this particular loop, then maybe I will just keep on going in the loop infinitely, right? So is it possible to have loops in this problem? Well, no. If you really look at it, if I'm going from 1 to 2, then 2 to 6, then 6 to 9, then the next number that I would like to go to is going to be greater than 9. So if I try to go to any number other than greater than 9, if I go to 9 again, it will not work, right? Because it is equal to the 9. If I try to go any smaller number also, it will not work because I want to go to a greater number. So it means we will not have any loop in this problem. So now let us try to figure out the most brute force way to solve this particular question. Now since we know that we have a matrix and we have to go through each and every path, we are going to use DFS, and this is a very standard algorithm. If you understand graphs, you will have to know this particular algorithm, otherwise you will clearly not be able to deal with these hard kind of problems, because it's kind of a mandatory for hard problems. So in the most brute force way, what we can do is we can take the DFS algorithm and run the DFS algorithm on each of these cells. So we can run out 9, 6, 8 and all of these cells, and what it means is that I will end up running DFS on all of these cells for m multiplied by n times, where m is the number of rows and n is the number of columns. M represents this length and n represents this length. And the time complexity of DFS itself is order of v plus e, right? So v is the number of vertices or nodes and e is the number of edges. So the total time complexity will be m multiplied by n whole multiplied by v plus e, right? So what is v? Well, v is the number of vertices, and how many vertices do we have? We have these many vertices. Each and every cell represents a vertex here. So we will have m multiplied by n vertices plus how many edges do we have? Well, in the question it is already told to us that we can go to left, right, up and down. So we have 4 edges because we are able to go to 4 direction, right, from any given node or any given vertex. So we have 4 edges. Now this 4 is per vertex. It means for each vertex we have 4 edges. So how many edges are we going to have for each and every vertex? We will simply do this. 4 multiplied by m multiplied by n. Simple as that, right? Now you may be saying that Satyam, no, this is not correct. You can go here and this is out of bound and this also is out of bound and we have multiple nodes like this. These are all out of bound, right? So these edges do not exist. And I will say, yes, they don't exist. But right now you are looking at a 3 by 3 grid. What if it was actually a million multiplied by 1 million grid? At that time, the vertices at the edges are going to be very less compatible to the vertices in the middle or anything in between. So in those insanely large data sets, this number is going to be very, very, very close to the exact number. And that's why we are going to take this number as the time complexity. So we will have here m multiplied by n multiplied by m multiplied by n plus 4 into m multiplied by n, which is going to be equal to m square n square plus 4 into m square n square, right? Which is going to be equal to 5m square n square, which is going to be m square n square in big O notation because we can remove the constant. So the brute force solution of taking the DFS algorithm and running it on each and every node and trying to go through all of the paths from each and every node in the matrix, you will get this time complexity, order of m square n square, or you can also call it order of m multiplied by n whole square. So now the question is, can we do better? And the answer is yes. Yes, we can do better. And we can do better by actually using the first observation that we found. So in the first observation, we know that we can find the longest increasing path from this cell if I just add 1 to the longest increasing path of the next cell, right? So I can just take the longest increasing path from the 2 here and I can simply say LIP of 2 and I can simply add 1 into it and that will give me the longest increasing path from 1. If I go in this direction, then only this is going to be the longest increasing path for 1. And so what it means is that I can simply go in up, left, right and down direction and get 4 different longest increasing paths. And then I can simply select the maximum between those 4 different longest increasing paths. I will get a longest increasing path from right direction, then for up direction, then for left direction and then for down direction. Just select the maximum of these, right? But how do we start this? How do we start storing all this stuff? Now, since we have a matrix and we have to store the values for each of these cells, we will also need to have a matrix of our own. So we will have a matrix like this. It will also be same dimension, that is 3 multiplied by 3 here. And now we can start storing inside of it. So what we can do is we can start with the 9 and we will try to find out the maximum path. If I go in this direction, I will get the same number, so I cannot go in this direction, right? If I go down here, I will get a lesser number or smaller number, so I cannot go here because I want the maximum increasing path. I cannot go up because it is out of bound. I cannot go left because it is also out of bound. So what it means is that I can only stay at 9 if I start from here. So the length is going to be 1, right? So here I can store 1. So the longest increasing path starting from 9 is 1. Then I will be here. So what is going to be the longest increasing path from here? Well, if I try to go here, I will not be able to do that because it is the same number. If I try to go here, it is a smaller number, so I cannot go here. If I try to go down here, it is also a smaller number, so I cannot go here. And if I try to go up, it is out of bound. So it means I will need to stay at 9 all the time, which means here also the length is going to be 1. Then I will reach here. Now where can I go from 4? I can go to this path, right? I can go from 4 to 9, and when I'm going from 4 to 9, I do not need to go from 9 to any other path. Why? Because I already have the maximum longest path starting from 9 stored. So what I can do is I can take the 4, okay, and then I can just take the path from the 9. So the longest increasing path on the 9 is 1, and I can simply add 1 into it, so I will get 2. And that is correct, right? Because the longest increasing path in this direction is going to be 2. So in the left direction, we have the longest increasing path as 2. Now we will have to go through other direction. If I try to go up, I will not be able to do anything. It is out of bound. So right now the maximum increasing path is going to be 1, right? So in the up direction, it is going to be 1. In the right direction, it is going to be again 1. Why? Because it is also out of bound. So right also contains 1. If I try to go down here, I will see 8. Now here for 8 we do not have anything stored. So what we will have to do is we will have to run the DFS on 8 and we will try to go here. This is the recursive DFS right now. So if I try to go to 6, I cannot go here. Why? Because 6 is smaller than 8. I need the greater number. If I try to go down, I will not be able to go down because it is also smaller. If I try to go here, I cannot go on the right side because it is out of bound. If I try to go up, since our algorithm is going to be written in a way that we will allow to go up, will I be able to go up from 8 to 4? Well, I cannot. Why? Because 4 is smaller, so I don't need to handle this particular case, right? because 4 is smaller, so I will not be able to go to 4 again from 8. So this is going to be handled automatically. So from 8, I was not able to go anywhere else. So it means the length from 8 is going to be 1. So it means the longest increasing path from 8 is going to be 1. So I can simply store that 1 here. And now I will go back to the 4 and I will add 1 to whatever path I got from 8. So it will become 1 plus 1, 2. So in the down direction, I will have a candidate of 2. Now here I just need to select the maximum of these. So the maximum is going to be the value 2. So I can simply store 2 here. Now as you can see here that we have been able to store 1 here also, right? We also had the same candidates for 8 also. I just did not write them down. The candidates were simply 1, 1, 1 and 1. Okay, that's why I did not write them down, because I did not need to write them down. That's why we actually selected 1 and placed that here. So now we have 6 here. If I try to go this side, I cannot go, right? Because it is the same number. So I will get a 1 here. Then if I try to go to left, I will again get 1 because it is out of bound. If I try to go down, I cannot go here because it is less than 6. So I cannot go here. So it is going to give me 1 again. Then if I try to go up, I can go because 9 is greater than 6. So the up is 1, right? So I can add 1 plus 1 is equal to 2. So I can store 2 here. And this is going to be 1 because we already calculated it right here for 8. Now this 6 is done. We will go to the next one. So for this 6, we cannot go in this direction because it is same. So we will get a length of 1 here. If we try to go down, we cannot go down because it is less. So we will get a length of 1 here again. If we try to go up, we will get a length of 2. Why? Because the up actually contains a length of 1. So 1 plus 1 is equals to 2, right? If we try to go to the right, then I will get a length of 2 again. Why? Because 8 have a length of 1. The maximum increasing or the longest increasing path from 8 is 1. So I will again add 1 to this path and I will get a path from 6. So this is 2, this is 2. Okay, so the maximum is simply 2. So I can simply write 2 here. And now this 8 has already been calculated right here. So we don't have to go through it again, right? Now we can go to the next cell, that is the 2. If I try to go right, I cannot do that because it is less than 2. So I will get a length of 1 back, right? If I try to go left, it is out of bounds. So I will get a length of 1 here again. If I try to go down here, I cannot do that because it is also out of bounds. So I will get a length of 1 from the down also. If I try to go up, I will see that 6 is greater than 2. I will check the matrix. So there is something stored in the matrix. So I will take the matrix value 2 and I will simply add 1 to it and I will get my path. So the maximum path from 2 is going to be 3. Now we will reach this one. If I try to go to left, I will get this 3. So I will take 3 plus 1, that is 4. So the left candidate is 4. If I try to go up, I will get this 2 here, right? So the up candidate is going to be 2 plus 1 is equal to 3. If I try to go down, I will not have anything. It is out of bound, right? So I will get 1 back. So the down candidate is going to be length 1. Now if I try to go right, it is same, so I cannot do that. So I will go back to the 1 with a length of 1. So the right candidate is also the length 1. So it means the maximum here is 4. So I will end up storing 4 right here. Now the only remaining element is this one. So if I try to go up, I will see that there is something stored in the matrix, that is 1. I will take 1 plus 1 is equals to 2, right? If I try to go left here, I cannot do that. Why? Because this is basically the same. So I cannot go to left here. So this will return a length of 1 here. So the left candidate is going to be 1. If I try to go down, I cannot do that because that is out of bounds. So I will return back with a length of 1. If I try to go right, it is also out of bound. 1 length again. So it means the up candidate is 2, the left is 1, the right is 1, the down is also 1. So the maximum is 2, so I will store 2 here. And this cell was filled with 4. I erased it by mistake, so I will just add 4 again here. And now our matrix is complete, right? Now we will take the maximum value in the matrix and that is going to be answer. So we can simply take 4 and answer is going to be 4. So this is how it's going to work. And so you can already see that we were able to reduce many recursive DFS calls by using the already stored values in this matrix. And that reduces the time complexity by a huge amount. But before that, let us look at the code. So this is the code. First of all, I'm taking the rows and the columns from the given matrix. This makes it easier to do calculations later on. I don't have to keep writing length matrix and the length matrix 0. And here is a DP hash map. You can also create a 2D array if you want, because that's what we discussed in the drawing explanation. But using a hash map feels more simple to me. Then we have this particular variable maxi. It is going to keep track of the maximum value that we have encountered till far in the execution. Then here is the DFS function. We are taking the row, the column and the previous value because we need the previous value to compare if we should run the DFS on the current value or not. If the current value is same or less than the previous value, we should not go ahead, right? So that's why we have previous value here. Then we have the non-local maxi. What we are saying is that we are going to access a non-local variable maxi outside of this function. And here are the base cases. So if the row or column is out of bound, we are going to return 0. Similarly, if the current value of the matrix is basically less than or equal to previous value, we are again going to return a 0 because we are trying to find the maximum increasing path. And the final base condition is that if we have already calculated the longest increasing path for the given row and column, and we have already stored it inside of the DP hash map, then we can simply return that value. Then here we are running the DFS call on 4 different directions. This is going to run the DFS call on the lower direction or the down direction. It is going to run it on up direction. This is going to run it on the right direction, and this is going to run it from the left direction. And each time we are adding 1 to the result that we got from the DFS call for that direction to get the maximum increasing path starting from the current node in that direction. And then we are checking if this particular length is actually greater than the current result. If it is greater than the current result, we will take that length and we will store it in the result variable. And then we will take the new result variable, and then we will go in the next directions. Okay, and then we will again make the comparison for this new result variable to the longest increasing paths present in the other directions. And then eventually we will have the longest increasing path stored in the res variable for this current node or this current row and column value. And then we will simply store this res inside of this DP so that we will be able to access this value later on in the code execution. And here we are making sure that if the current result is actually the maximum result that we have found so far, then we will actually update the maxi variable also, because this is going to contain the answer because it is actually tracking the maximum that we have seen so far. And here we are simply returning the result, ending the DFS call. And now here I'm running a loop on rows and the columns of the matrix to go through all the elements that are present in the matrix, and I'm trying to run a DFS on all of them. The reason this works is because if we have already gone through this particular row or column and we have already stored the value in the DP, this first base condition will hit the second we start the DFS, and we will return immediately. We will not go to this particular section ever. So that's why this works. And now at the end we are returning the maxi because we actually kept track of the maximum length that we got so far. So maxi is the answer and we will return that. So now let us run it and see what happens. So our solution runs in 194 milliseconds and beats 27.58% solutions on Leetcode, and that's pretty much as efficient you can get about it. And also you cannot really trust these numbers all that much because they change each time you submit the code. So now let us look at the space and time complexity for this particular solution. So the space complexity is order of m multiplied by n because we are actually creating another matrix or hash map that will have the same size as the given array, because we will have to store values for each of the cells in the given array. So this will contain m multiplied by n elements, hence we get the space complexity to be m multiplied by n. But the main thing is time complexity, and right now it is m multiplied by n. Earlier it was actually square of m multiplied by n, but right now it is simple m multiplied by n. So how did it reduce so much? Well, before making this video, I saw one of the Leetcode's video on this particular problem, and there he is actually explaining one of the best intuitive ways to understand it. He is simply taking two cases. In one case, every element is going to be the same, right? It is going to be 9, 9, then here also 9. So here we have 9 in each place. It means we will have to run DFS for each of these values, and we will get 1 as the length for each of these values. So in that case, we will end up running DFS. Okay, DFS will be run for each of these values. And how many values do we have? We have m multiplied by n values. So DFS is going to run m multiplied by n. And there will be no recursive DFS inside of any DFS call because all of them are same, right? So I cannot go in this direction or in this direction or in down direction or in up direction. So it means I will always be on the same cell. Why? Because all of them are same and I need a greater element, not the same element. So in this case, the DFS is running m multiplied by n times. Now the other edge case is that all of them are actually increasing 1, 2, 3, 4, 5, 6, 7, 8, and 9. So it means I can start from the 1 here, okay, and I will run the DFS. I will have a recursive DFS from the 1 then. So I will go to 2, I will run a DFS here, I will go to 3, I will run a DFS on this one, I will go to 4, run a DFS here, go to 5, run a DFS here, go to 6, here also I will run a DFS recursively, go to 7, DFS, then 8 also will be actually called, then 9 also will be done. So it means after starting DFS from 1, I will end up going through each and every cell inside of this grid, right? So it means this particular first DFS call actually costed m multiplied by n recursive DFS, right? This is the recursive DFS count. But the thing is that now you don't have to run the DFS for any of these other cells. Why? Because they have already been calculated and stored inside of this grid somehow. So it means the DFS calls for each of these cells is going to take order of 1 time complexity now. And in the smaller example, this might not be very accurate, but when you are going for 1 million by 1 million cells, right, or 3 million by 3 million cells, well, at that time, this is going to overtake this order of one time complexity by a huge margin. So at that time, we can directly say that it is order of m multiplied by n time complexity. So this is an intuitive way to figure this out. If you try to go for mathematical way, that can actually get very complicated. So yeah, that's why I'm not going into the mathematical proof, but you can of course go ahead and learn it online. I mean, there is ChatGPT and Gemini available at your fingertips all the time now. And so that is why the time complexity is order of m by n. So yeah, like the video, subscribe the channel. If you have some kind of question that you would like me to target, or you have some kind of topic that you would like me to talk about, just let me know in the comments. Now we will meet in the next video. Till then, bye.